Okay, so welcome to this second webinar to help you prepare a James Webb proposal. Today, Julien Rameau and I will give you an overview and a demo of the tools at your disposal to plan and prepare James Webb's observations and a proposal. This is a first broad look at the tools. We'll go into more details in future webinars, but for now it's really a broad look just to give you an idea. I thought I'd present ourselves first. We will both be presenting today. I am Loïc Albert, and my teammate here is Julien Rameau. We are both research associates at the University of Montreal. Our job is to serve as instrument scientists for James Webb for the Canadian community. We also serve as resources for you, the Canadian astronomers, when you'll need help preparing James Webb proposals, or in the future for processing the James Webb data. So do not hesitate to contact us for anything James Webb. Okay, so today is a full-packed webinar, and I'll give you this note. Contrarily to future webinars, we actually do not recommend that you open your own local window and of the tool and to follow what we do. Instead, just sit back, watch the screen, and relax, and let's start. Let's get acquainted with James Webb tools. Okay, so what is the #1 tool? It's this one. It's JWST. It's a website maintained by the Space Telescope Science Institute, the STSCI. That's where all of the documentation resides. And that's the #1 spot you want to read when you have any question. So please don't fall in the bad habit of not going there. When all else fails, read the manual. No, go read the manual first if you can. If you have any question about the instruments, about the astronomer proposal tool, any tool, that's where you should go. Okay, so this webinar has 5 sections, and I'll do some, and Julien will do others. So the first thing is a reminder of what is the field of regard, how much of the celestial sphere the James Webb can see. So as you know, James Webb is at the L2 Lagrange point, and it's pointing away from the sun. That is, there's a sail that blocks all of the heat to keep the instrument cool. So in order to be always in the shadow, the telescope has minimal movement. So it can tilt by about 45 degrees. And also it can turn about its rotation, about the axis between the sun and the spacecraft by 360 degrees. Which means that at any given moment, James Webb can point for about 40% of the sky surface. In order to cover other parts of the sky, you need to wait for the observatory to revolve around the sun, and in doing so, it will swap twice about every target on the sky during a year. In addition to the 2 rolls, there's this roll. There's a roll, plus or minus 5-degree roll that it can do at any given day, which means that at any given day you can observe a target with a position angle that's plus or minus 5 degrees. All right, so I thought there's a tool called the Target Visibility Tool that exists to help you know if your target, when your target is visible, for how long it's visible. It's okay. So let me first state that this visibility, target visibility feature exists in the Astronomer Proposal tool. Okay, that's the official software that you use to submit a proposal and plan your observations. It's there. However, it's burdened. You have to enter various fields before you access this capability in APT. So that's why there's an independent Python-based tool that's simpler to use, and you can only address this question of visibility. And it's distributed in the AstroConda package. The target visibility tool returns two things. It gives you when in the year is a target visible, and it gives you the position angle of the target in your field of view. So it's basically the position angle or of the aperture of the detector on the sky. There's also a second Python-based tool for coronagraphy that we will not cover today, but in webinar number 8. All right, so you can install the TVT, but I will not go into this, but you can look and install it for the next webinars. Also, I talked about the position angle, and here's what I mean by position angle. Here's a definition, a footprint of all the instrument field of views in the focal plane of James Webb. And here are a few important things to keep in mind. First, the reference coordinate of James Webb is called the V3 position angle, V3PA. Okay, it's the angle relative to north, celestial north, that the observatory as a whole is pointing towards. So, if your V3PA is 0, then you're pointing north. All of the instruments have their own aperture position angle. Luckily, most of the instruments' aperture position angle is aligned with the V3PA, with the observatory position angle. There's only NIRSPEC that is different. It has a 138 degree rotation. So you need to keep this in mind when you plan your observations, because in the APT, you enter the V3 position angle as the angle that you want your target to be observed at. Okay, so let me give you an example, basically, of the visibility tool and how you select the position angle. Okay, so I'll go open a browser and use EasySky. EasySky is a web application where you can view the entire sky. And what's neat about the EasySky is that I'll show you in a minute. So let's say I want to observe NGC 891. NGC. It's a nice edge-on galaxy. So what's nice about EasySky is that you can overlay the footprint of the James Webb instruments. So let's say I want to image my target with NIRCam, the imager. So I would like to show here there. So let's say I want to image this galaxy. Okay, I would like to say measure the stars in the galaxy, measure their brightness. So I will try to center and rotate the field of view of NIRCam. NIRCam has two modules that you can see here. And they can be used in both at the same time. And each module has looks at two wavelengths simultaneously, a red channel and a blue channel. So I would like to cover as much of the galaxy as possible, so I will offset and rotate the galaxy, the field of view on the galaxy. Okay, so you see there I did an offset, and let's see what's the best optimal rotation. 100 degrees, pretty good. 115, I think, is the best. Yeah, 115 is great. Obviously, you could do 295 degrees, and it would do the same. Okay, so we basically want the position angle of the NIRCam apertures to be aligned at 115 or 295. Okay, so is this possible? Can we do this with James Webb? That's where the target visibility tool becomes important, becomes interesting. Okay, so, well, I'll just install source activate, use the target visibility tool here. It's in AstroCanda. Okay, there, and now I type JWST, General Target Visibility Tool here, and I will give it my RA deck of NGC891. Okay, and I'll actually use this option of saving the ASCII table output instead of showing it in the window. There. So this tool produces a nice plot. Okay, in the plots here you have basically the position angle available as a function of date. And you have it for V3PA, that is the observatory reference coordinates, as well as all of the aperture position angles of all 5 instruments. And you can see that, for instance, NIRCam and the V3PA basically have the same values because they are pretty much aligned with each other, but that NIRSpec has different position angle. Its aperture position angle is different. Okay, so let's zoom in the cycle 1 time frame in 2019 for NIRCam. Okay, so we see that there are 2 windows of opportunity of visibility for NGC891. You can observe it in around, say, August or around December. In the August time frame, the position angle available are between about 215 and 255 or so. Remember, we want to observe this target with a position angle of 115 or 295, so this window is probably not good. We will not be able to align the NIRCam field of views on the disk. If you look at the second window, we'll zoom on it. There you seem to have the possibilities are between about 60 and 105 degrees in position angle, which is much closer to what we wanted. We wanted 115. So probably here at the end of December is when we'd like to observe NGC891. Okay, so you will notice here that in this plot there's a width to this distribution, and the width comes from the possibility of doing a plus or minus 5 degree roll of the spacecraft at any given day. Okay, so if you wanted to know exactly in more details what's to the decimal point the position angle that you can access, then you look at the ASCII table that was produced. Okay, so in this table, you have basically header lines, but what's interesting is those lines here. You have the dates and all the position angle available. So let's look at the observatory position angle. That is the second and third columns. That's the angles that you can observe at those dates. So if we go to cycle 1, that is December. So we said 2019 around December. That's it here. So we see that you can observe between 90 degree and 105. So let's use that as a good valid range for our observations. 90 degree to 105 can be observed down to about here, January 7. You can still access 90 degree. And the window started in about December 19 here, where you can have between 90 and 105. Okay, so it's basically 2 weeks during which you can observe this target. All right. So that basically covers this visibility tool. And so let's move on to the next section of the presentation. It's basically basics of the infrared detector readouts. James Webb is using infrared arrays, and if you're used or accustomed to CCDs, infrared arrays are read out a bit differently. And all of the jargon associated with how you read such array is present throughout the exposure time calculator and the astronomer proposal tool. So you need to have an idea how they are read out to properly use those tools. Okay, so if you're used to a CCD, here we have the number of photons or electrons that you detect as a function of time. And you start detecting those when you obviously open your shutter, and then you stop detecting when you close the shutter. And after that, after the shutter is closed, well, you read out the detector, and you do so by moving all the charges from one pixel to the next until you reach the amplifier. And that process basically destroys your image. You can only then read it once. So it's a destructive read. Something to notice as well for CCD is that their bias level, that is the structure that you see on a 0-second frame, is very smooth, very nicely behaved. It has very small amplitude. I'll show you in a minute what I mean by that. For infrared detectors, the process is different. There is no shutter on infrared detectors. Okay, so the detectors and pixels always see photons coming. So how do you set the integration then? Well, it's between when you reset the detector and when you read. So I'll show you a bit what I mean here. An infrared detector can also access every individual pixel directly without destroying its information, without moving charges. So that allows to have non-destructive reads and do multiple reads of your image as you integrate. Okay, so that's why you have multiple reads, because you're not moving charges around, you're just sampling the voltage value. And also another feature of infrared detectors is that a single read, a single image looks horrible. It looks really bad because it has a lot of structures with several thousand ADUs peak to peak. So it doesn't seem nice at first look. So here's what I mean by that. Okay, on the left you have a bias of a CCD here, Megacam. You see that the bias is basically smooth, close to zero, very small amplitude features, and so you can imagine an astrophysical scene on top of that, and there's no noise essentially related to the detector. However, on the right you have a NIRISS, so James Webb, individual read, and you see lots of structures with large amplitudes. And a faint target on this would be lost in what looks like noise. It's not actual noise, it's a pedestal, and luckily this structure disappears when you subtract two consecutive reads. The structure disappears and it doesn't introduce noise. It's just there, and so that's why you need to subtract two consecutive reads to remove it. All right, so how exactly is an infrared detector read or reset and read? Here I will show you a step by step. The first thing is that the first pixel on the array is reset. You go pixel by pixel. You cannot access all of the pixels at the same time. So you do it sequentially across all the array. So the first pixel is read, then is reset, sorry, and then you proceed to the next pixel that you reset, and so on until you've reset all of the pixels, during which the first pixel has started integrating light. Okay, so when you reach the end of the resetting, you do the first read on the first pixel, and the last pixel that has just been reset is starting to see light. And then you do, after some time, you do a second read on the first pixel and a third read, and eventually you have to proceed with all the third reads of all pixels, and you have read all of the pixels for a third time. At which point the exposure stops and you do a reset on the first pixel again, and the cycle starts again. So the measured flux is the last read minus the first read. Okay, and a frame time is basically the time it takes to cycle through all the pixels to do a read or a reset. And the frame time is dependent on two things. Well, one thing, the number of pixels that you read and the time you take to read it, and it's constant. That time is constant. It's 10 microseconds per pixel. So if you, for instance, wanted to change the integration time, okay, the two things you can do is, first, you can read out the array more or less time, or you can change the subarray size. You can change how many pixels you read to change the frame time of any single image. All right, so what follows applies to near-infrared detectors, the NIRCam, NIRSPEC, NIRISS, FGS detectors, but the MIRI detector is a mid-infrared detector, and it's slightly different. And I mean, the jargon is the same, the JWST jargon is the same, but the exact process is a bit different. But basically, here's where the jargon, James Webb jargon starts. In our jargon, each read is called a frame, okay? And it represents, yeah, all the reads. And the number, you can average different frames into what's called a group. Okay, and that's why would one do that? It's basically to reduce the volume of data that you download to ground. You cannot download all individual reads. You have to. There's not enough throughput, so you have to average some frames. If you use NIRCam for other instruments, you may be able to download all the images, but NIRCam produces a lot of data. Okay, so each group is an average of frames, and you have as many groups as you need to do an integration. Okay, an integration here is basically what we are used to as an exposure for CCDs. It's how long you integrate before resetting. It's also called a ramp, and the length of the integration is basically set by what is your saturation. If you're looking at a bright target, you want a short integration, or if you're going to do deep fields and you don't want to integrate too long because cosmic ray may start to impact your images. And you can basically have multiple integration in an exposure. An exposure is the actual FITS file that's saved, and you can have many integration in that exposure if you want. You can also think of the exposure as a ditter position. If you ditter around. All right, so that covers the first part, and we'll move to the exposure time calculator tool that Julien